We finished the first video by foiling right here. And hopefully you understood that. Just, making the I squared -1 so that you can combine the real parts. Positive 12 plus 6 is 18, and then we had the minus I. 4 plus 3I squared is no different than 4 plus 3x squared. Except, of course, it's not x, it's I. So in the end, I'll have an I squared to deal with. But what I mean is, it's not like you just square each term here, okay? What we have to do is foil this. 16 plus 12i plus 12i, that gives me 24i plus 9i squared. Plus 9i squared becomes minus 9 because I squared is -1. So we end up with 7 plus 24i. Okay? Here we're going to have, this is nice, plus and a minus, same terms. It's looking like difference of two squares type thing. We have 36 minus 30i plus 30i, that's 0 i's, minus 25i squared. Well, I squared is -1. So we really have 36 minus -25, or 36 plus 25. And look, we get a real number. We multiplied two imaginary complex numbers together and got a real number. Okay, that's why Rene Descartes invented them. So that we can stop having to say, oh, no real answer, guess we have to quit. No, mathematicians don't quit. Okay, so now we're going to multiply by 5 plus I over 5 plus I. Why? Because I want to get rid of the square root. I is the square root of -1. We get rid of the square root of -1 in the denominator. And we just saw up here that if you multiply by conjugates, you'll end up getting a real number. So up top, I have to FOIL. I have 15 plus 3i plus, 10i. That's 13 i's plus 2i squared all over 25, my middle terms cancel, minus I squared. 2i squared just becomes minus 2. So 15 minus 2 is 13. I have 13 plus 13i. I squared is -1, so I have 25 minus -1. That's 26. Well, 13 goes into 13, and 13 goes into 26. So we have 1/2 plus a half I, or just 1 plus I over 2. I don't really care which of these forms you use. If they want complex number form, they will want you to write the real number part and the imaginary number part. Here I'm just going to multiply by I over I to get 3i over I squared, realizing that I squared is -1. So yes, I don't have a denominator with I in it. And that's what we want, because we're not technically supposed to have denominators that have square roots in there. If we look at this pattern, I know that I is I. Right, there isn't really much we do with that. It's the square root of -1. We just call it I. When I square that, I get -1. I to the third is it's really I. Think of it this way. It's I squared times I. Isn't that I to the third? I don't know why I wrote it like that. That looks terrible. I squared times I is I cubed. So I squared is -1. I end up getting -1i. Or we just say -I. I to the fourth is I squared squared. That's -1 squared. That's just 1. I to the fifth is I to the fourth times I. I to the sixth is I to the fourth times I squared. I to the seventh is I to the fourth times I cubed. I to the eighth is I to the fourth squared. So since I to the fourth is just 1, this becomes 1 times I. So that's just I. This is 1 times I squared. That's just I squared, which ends up being -1. 1 times I cubed, that's just I cubed, which we just saw was -I. I to the fourth is 1. 1 squared is 1. I to the ninth, well, that's I to the 8th times I to the 8th times I squared. Okay, and remember, I to the 8th is 1. So again, this becomes I, negative 1, negative I, 1. Do you see the pattern? Every 4th time, the answers, when I reduce these, are either going to be I, negative 1, negative I, or 1. Those are my answers, okay? Depending if you have I to the 1st, that's just I. Okay. What you do is let's just try this, I'm sorry. If I have I to the 430th, and I know it repeats every 4, then I'm going to take 4 into 430. That goes 107 with a remainder of 2. Okay? Now, you have to be careful, all right? Sometimes people use their calculator. Let me pause this and get my calculator. So if I would have just taken 430 divided by 4, sometimes people are like, oh, well, my remainder is 5. No, okay? It's 107 with a remainder of 2 because you were dividing by 4. So it's 0.5 is 1/2, right? Be careful. This at least will give you the 107, and then you have to figure out what's left over. Okay, it's a remainder of 2, so I to the 430th is the same as I squared, so this is just negative 1. I to the 59th is 4 goes into 19 4 times, remainder of 3, so this is the same as I cubed, which we know is negative I. 92, 4 goes into 92. Remainder of 0. Oh, I said 1, 2, 3, or 4, but think about it. When I divide by 4, I'm not going to have a remainder of 4. Okay, a remainder of 0 means, well, it's the same as I to the 4th. Think of it as I to the 0. Anything to the 0 is 1. Maybe that, if you're thinking this is the exponent that goes on I, right? The remainder is the exponent that goes on I. I to the 430th is the same as I to the 2nd. I to the 59th is the same as I to the 3rd. I to the 92nd is the same as I to the 0. Okay, so we just get 1. Okay. Now, you guys with your fancy dancy calculators, I would be remiss if I didn't show you. You do actually have I on your calculator. Do you see it down here? So I guess I could go I. Here's what happens though. I go I to the 430th. The answer is supposed to be I squared, negative 1, right? Our calculator messes up a little bit. I did get the negative 1 minus 3e to the negative 12, whatever this means, 0.12 zeros, 0.000000000003i. Calculator messes up the 0, guys. There is no, this is negative 1 minus 0i. In other words, negative 1. If that's going to mess you up, sometimes the calculator messes us up on these, okay? If I do I to the 59th, what's that give me? It's supposed to give me negative I. It gives me, do you see that this number is 0? This gives me 0 minus I. Well, that's negative I, but you have to recognize this as 0. Negative 1e to the negative 13th is 0.000000000000001. Might as well be 0. I don't know why the calculator does, whatever, however they program this, they mess it up. I to the 92nd. I did want to show it to you, though. If you can recognize that that's 0, then you're in good shape. That gave me 1. Gave me 1 minus 0i, but that's 1. Okay. All righty. That's it. Good luck. Let's move forward to 8-2. Okay? 8-2. I didn't start at the right spot. Here we go. 8-2, if you have your notes. we're going to graph complex numbers. It's exciting. We just switch around. We have the real axis and the imaginary axis instead of the x and y axis. The horizontal axis we call the real axis. The vertical axis is called the imaginary axis. The complex numbers are graphed in this complex plane. Okay? We just take, look at, we're taking.
Interruption. The varsity softball game starts.
Okay, so look what we have, a vector. Okay, each complex number determines a unique position vector with initial point at 0, 0, and its terminal point at A, B. Okay, so look at 2 minus 3i. We plot the point 2, negative 3. Okay, 2 is my x and negative 3 is my y. And then I go from 0, 0 and draw a vector. This is the graph, the vector that represents 2 minus 3i. Okay, so let's look at adding these together. The sum of 6 minus 2i and negative 4 minus 3i. If I graph that, this is so fun. We go to 6. 1, 2, 3, 4, 5, 6, negative 2. Okay, and then I'm going to make, well, 1, 2, 3, 4, 5, 6, negative 2. And I make my vector. There we go. Vector. Magnitude and direction. Okay, then we graph negative 4 minus 3i. And I graph that wonderful vector. Okay, and the resultant, remember, we end up making a little parallelogram from this. Well, the slope of this was down 3 over 4. So from here, I'm going to go down 3 over 4. So I can make that parallel, make sure it's parallel. Okay, and then same here. This was one down 2 over 6. What's that? Down 1 over 3, let's say. Okay, so I'm going to do that. Down 1 over 3. So let's make that nice little vector. Okay, the resultant is right here. Let's see, where did that end? 2, negative 5. Okay, let's go back and see if I would have just added it together. We learned how to add these together. Let's see, that part 2, and then the, oh yeah, minus 5i. Makes sense. Okay, I got 2, negative 5. And I got this, all right? See? The graph of it makes sense to how we add, subtract, right? Okay. We learned this before. We've been on the unit circle where r was 1. So we just said cosine theta is x. Actually, remember, okay, cosine of theta is actually x over r. All right, we've been using the unit circle where the radius was 1. Sine theta was y over r. R, of course, is the square root of x squared plus y squared. We've done this. Theta is, tangent is opposite over adjacent. It's y over x. Okay? This is, they take those same things. Okay? Here's OP. And we are now going to substitute the new x and y formula into x plus yi. Okay, this is x plus yi, right? That's what we were just talking about. It's the a plus bi, x plus yi, whatever you want to say. Okay, but here are the new ways to say it. Okay, if I can just get rid of this. Okay, anyway, x equals r cosine theta. Well, no joke. We used to say cosine theta was x over r, so I'm just multiplying by r. X is r cosine theta. Y is r sine theta. These are still the same. Nothing's changed. That's what we used to say about that, and that's what we're still saying. Okay, so write that all down. Okay, those are our new relationships that go to our trig or our polar form of a complex number.